Hello, my name is Mihai Trăscău and I will present our work named IntAli, which was developed in the IMAS laboratory of the National University of Science and Technology, Polytechnica Bucharest. According to the World Health Organization, the trend for poor dietary choices is increasing, even while this has been identified as a leading risk for various diseases. Our hope is that we can leverage computing technologies that can, for example, analyze the food intake and dietary habits of users to help them make better and more balanced choices in their daily diets. There are many ways we can create an impact with technology on this matter. At the base of all such solutions, or at least as an integral and important part of it, stand automated food and ingredient detection methods. These help by identifying food items that are added or removed in monitored spaces such as a fridge or a pantry, giving access to various other tasks. For example, alerting about food that has gone bad, recommending recipes based on available inventory, and medium to long-term monitoring of dietary habits of users. Therefore, we need solutions that can reliably recognize food and ingredients, even in difficult conditions, often found in real-world scenarios. For example, it is to be expected that fridge or pantry shelves contain many items, resulting in cluttered scenes that are often difficult for computer vision methods. Diverse backgrounds and lighting conditions add to the complexity of the problem, while robustness to item variance also constitutes a big challenge. Think of how many variations appear in apples or how half cabbages look relatively to whole ones. In line with this view, we have decided to collect and annotate an image dataset containing food and food ingredient images taken by volunteers with their own smartphones from their own refrigerators, pantry shelves, or tables. Moreover, once this dataset was collected, annotated, and validated, we have analyzed the feasibility to train or fine-tune a model using the collected data. Our crowdsourced dataset contains almost 4,000 images with about 12,000 items segmented in 165 classes, plus a special class for rare items. All in all, 10 major food categories were observed. The categories covered in the dataset were proposed based on the analysis of several recipe sets. Data collection was instructed based on these categories, ensuring that volunteers only capture images containing items pertaining to the specified categories. Occasional rare items were subsequently added to a separate others category. As you can see from our post-collection analysis, spices and flavorings lead in number of items per category, which is to be expected due to this category of products being packaged individually. Think of oregano, thyme, parsley, chili, etc. Then, vegetables and fruits have been found in a larger variety as they constitute base ingredients for many types of prepared food. Least representative are half-cooked meals, which are not necessarily popular in the geographical area where the dataset was collected, and drinks, which include some types of juices, sodas, and non-dairy based liquids. Here we see that the distribution of image size is spread between 1.5 and 8 megapixels, the usual range we expect from mid-range smartphones. Even though the majority of images have a high pixel count, as you will see, the studies for automatic detection of ingredients that we have performed indicate that low resolutions are also feasible. So the optical hardware that could be used for implementing AI-based solutions is less constrained in terms of performance, therefore more affordable. To summarize on the data collection and annotation process, it's worth mentioning that the diversity of the collection stage was ensured by instructing the volunteers to provide images using their own equipment with the ingredients and food items they had at hand, and without any special consideration to lighting condition, angles, or distance. However, the data collection guide we provided did restrict them to previously mentioned food categories and instructed about the acceptable range of items in the image. In the annotation stage, we have used CVAT to segment each relevant item in the images. The annotation stage was also performed by volunteers, for which we made sure the allocation was randomized to reduce bias. Lastly, the research team has closely validated all results to ensure that the dataset has the highest possible annotation quality. You can see on this slide a couple of examples of annotated images from the dataset. On the left, there is an image from a fridge shelf, and on the right, an image from a set of items placed on a table. Analyzing the obtained annotations, we found that the histograms for number of instances per image and number of unique ingredients per image have quite a long tail. This suggests that although cluttered images do appear in real households, they are not really all that common. However, that might be misleading when analyzing food items detection methods, since the scene complexity is obviously much higher for such images due to partial occlusions and overlaps. Comparing our proposed dataset to other available public datasets, the first thing to note is the fact that our images are focused on food ingredients as opposed to cooked meals. This type of data enables more solutions to be developed, like recipe recommenders and groceries tracking. Moreover, the annotations our dataset provides are more informative and precise, being based on instance segmentation. For the benchmark, we have selected some state-of-the-art segmentation models that we trained in similar conditions with the proposed dataset. We use various augmentation techniques as well as the same class imbalance solution for fair comparison. We consider the MAP metric for evaluation since it's popular among segmentation solutions. As the results suggest, solutions based on InternImage were the most competitive. Of course, the increase in number of parameters for the Cascade Mask RCNN solution helps, but given the current size of the dataset, we have not attempted to train much larger architectures due to the risk of overfitting. Qualitative results show that the models managed to correctly pick up the items in the foreground, even in more cluttered scenes, while ignoring other items that are only partially visible or too blurry. However, there are still cases where, due to harder conditions like bad lighting, the tested models don't manage to pick up all the items in the image. You can see an example of that on the last row of the slide. To summarize our contributions, we have collected, processed, annotated, and analyzed a unique image dataset containing food and food items usually found in regular households. We have also provided relevant benchmark by evaluating segmentation models on the collected data. In conclusion, our high-quality dataset proposes denser annotations based on instance segmentation, which allows for more accurate vision-based AI solution. We have made the dataset publicly available on Kaggle. You can find it at the link on the slide should you wish to explore it and use it in your own research. Our future work on this project is focused on solving the long-tail distribution problem identified in the dataset by employing various techniques for data augmentation and loss function design, among others. Moreover, we think great benefits will be obtained by further collecting and annotating data. This time, it would be ideal to span the data collection stage across multiple periods to mitigate seasonality biases, and from more diverse demographics to ensure a better distribution across food items. Last but not least, more alignment with popular recipe databases will allow specialized vision-based food item detectors to have more impact further down the pipeline of an AI solution. Thank you for your attention. If you have any questions, remarks, or requests, please send them to the email address on the slide.